Okay, good morning students. Let's get started with today's class. So in the previous class, I know that was quite some time back, we were looking at this, the underdamped system, and I'm just going through last class notes, right? So what do we mean by an underdamped system? When this, the quantity which is under the radical sign, that is negative, which basically means that alpha is smaller than omega naught. So then what happens? This quantity, it becomes complex, right? So we write this as minus alpha plus or minus j root of omega naught squared minus alpha squared, and this term is called as the natural resonant frequency here. Okay? And so we developed the solution. We said that it comes as v of t is equal to the real number, the real part of it comes separately. Yeah, I've started the recording. Yes. So the real part comes off separately, and then we look at the imaginary part. Now this can also be expanded as, or this equation and the next equation, these two are equivalent. Okay? So if you have doubts, you can kind of evaluate, and you can see that both of them are basically you're just adding and subtracting terms to make both equal. Okay. So this helps us to reduce it to some constant times cos omega dt plus j some other constant times omega dt. Okay. Now we saw that this also can be written as some real constant time a1 plus a2 becomes a real constant times omega cos omega dt plus another real constant times sin omega dt, and this is where we had some confusion in the last class. So it turns out that if you take a1 and a2 to be complex conjugates of each other, okay, a1 plus a2 becomes a real number, and j times a1 minus a2 also becomes a real number. Okay. Now the thing is, it turns out that if you assume a solution of this form, okay, where you have e to the power of minus alpha t into a real constant times cos omega dt plus another real constant times sin omega dt. This also happens to be, this is also a solution. As I mentioned, if a1 and a2 become complex conjugates, then this is a solution, and this is a valid solution, and this is what is observed in practice. In other words, you can write the solution in a generic form as e to the power of minus alpha plus a cos term and a sin term where the coefficients end up being real. Okay, and this is good enough for our solution, and even in practice it has been shown that this is a valid solution. So we note for a parallel RLC circuit, we have alpha is 1 by 2 RC, omega naught is 1 by root LC, and therefore all our job basically is to find out what is the constant B1 and B2. So we took up this example in the last class, where it is kind of the same example that we had from the beginning. Okay, we did this for the overdamped system, we did this for the critically damped system, we also did this for the, we are also doing it for the underdamped system. If you kind of just flip back through your notes, you will see that this parallel RLC has the same L and C values, and the only parameter which is changing across the three systems is only the resistance value. For the overdamped case, we had a lower resistance, and for the critically damped case, we had a certain resistance value, and now we are using a little higher value. Okay, so first let's get it. Let's solve this system. So I think we did attempt a solution, right? So beyond this point, it's pretty much the same thing. You basically write, you take the initial condition. The initial condition was V of 0 is 0 and I of 0 is 10 amps. You substitute and you get the answer, and then you do a derivative, and then you extract the answer. So this is what we did in last class. So let's try to do one more problem today. Okay, and before we move over to the forced response cases. Okay. Just a minute. All right. So let's continue on our discussion with the underdamped systems, right? Let's try to solve another problem. Or before we solve this problem, okay, I want to kind of take it forward from where we stopped last class, right? So our expression was something like this, right? V of t was some 210 root 2 e to the power of minus 2t sine root 2 t. Okay. So how can we write the response? Or rather, how can we graphically sketch this?
The sine with frequency root 2 having an envelope of e to the power minus 2t.
Exactly. So basically, we can think of it as having being something like this. We know that v of 0 is 0, right? So it is going to start from here. This is time t, okay? And now we have only one sinusoidal component, and so it is going to be a kind of something like this, okay? And it's basically going to have e to the power of minus 2t. Okay, so probably my way of drawing it is not good, but let's just say this is your e power minus 2t curve. Okay, so the envelope, right? I think this you have done in Dr. Sudarshan's class, right? So the this is a sinusoidal signal where the amplitude, the envelope has got a exponentially decaying response. Okay, so if you compare this with in fact, the comparison becomes even more accurate, even more apparent when you do a forced response, which we'll do in some time, hopefully in today's class. So what happens is, like, as you keep when you go for a overdamped system, you never had so much of wiggles, right? You just basically had one, the overdamped system, I think would have looked something like this, or rather not even like this, maybe like this. That's it. And the critically damped system may have been something like this. Doesn't go negative, right? So it would have had been something like this. All right. So what we see here is the L and the C values remain the same. Okay. Only the resistance has been changed for all the three examples. Right. So for an overdamped system, the thing is it's kind of slowly settles. Maybe I should draw it a little. Let me just draw it like this. And then it just goes down to 0. It does not go negative. Okay. So it just goes up and then it just tangentially hits 0, right? And whereas for the critically damped system also, probably you have a little faster settling, right? I think we looked at settling time and all that, right? So how much time does it take to reach within 1% of the maximum value? You calculate the V max, and then you find out how much time it takes to settle within 1% of V max, and we saw the settling time. Now, if you take this underdamped system, for example, okay, now what happens is it takes a longer time to settle. And how much longer time does it take? It depends on this value alpha. Now, what is the value of alpha? Alpha is 1 by 2 RC. Okay. Now, as you keep increasing the value of R, okay, if you increase the value of R, what happens to alpha?
It will decrease.
Alpha will decrease. Now, if alpha decreases, now V of t, the generic form can be written as e to the power of minus alpha t into some b1 cos omega dt plus b2 sin omega dt. So basically you have a sum of two sinusoids, okay, that's fine with the same frequency. One is just both are out of phase by 90 degrees, okay, and then the envelope is dependent of e to the power of minus alpha t. So what can you say if you increase r and thereby alpha is going to reduce, does it lead to faster settling or slower settling?
Slower settling.
Slower settling, okay. Why slower settling?
Because
Basically it
alpha
is
is
going to, yeah, the envelope is going to very gradually reduce. That is, if the value of alpha reduces, e to the power of minus alpha t is going to have a more gradual slope, right? And because of this more gradual slope, you'll have more of these oscillations or what is called as ringing. Okay. In fact, see, right now you are studying about second order systems in terms of R, Ls, and C. Okay, and you know that it is a second order system because it has a the differential equation has a second order to it, and then you have two poles to it, right? S1 and S2. Now, I think you have not yet come across poles and zeros, but at least by the end of the course, we'll kind of tie both streams together. So you are looking at the frequency domain analysis in Dr. Sudarshan's class, and we are looking at the time domain analysis in my class. Okay, at some point of time towards the end of this course, we are kind of going to merge the two. Okay, and see how if you change a certain parameter, for example, in this case, if alpha is changed a little bit here, okay, what does it mean in the time domain and what does it mean in the frequency domain? So that kind of a link we will establish probably sometime soon, okay, and so that time it will make very good sense. So right now what we are seeing is, the point that I was trying to make is, it is not necessarily that only a RLC circuit, either a series RLC or a parallel RLC, it is not necessary that only these circuits should have this kind of behavior. Okay. In practice, what happens is you can take any system, okay, and when you write its transfer function, maybe in the S domain or S domain in the Laplace domain, or if you write the integral differential equations which govern its behavior, if it happens to be a second order system, okay, it will have this behavior. Okay, so it is not necessarily that it has to be an RLC circuit. In fact, what happens is in analog IC design or in analog design, when you do circuits from when you design op amps and so on, and op amp based circuits and so on. So when your filter or something like that has a second order transfer function, okay, so the same kind of behavior happens. There you will not have any inductors. You will only have op amps and resistors and capacitors. It will be a two pole system, okay, and two pole system, a second order system will have this kind of a behavior. This behavior is not restricted to RLC. We are just studying it in the context of RLC, but this behavior happens all across different systems and not even restricted to electrical systems or electronic systems. It happens even in mechanical systems. Okay. So, for example, if you talk about the suspension of a vehicle or a car or a bike, okay. So, if it's a second order system and you have an underdamped response for your suspension system, then what happens is, if you take your bike or your car over a hump, it will keep oscillating for a long time. Okay, so a hump in the road is like a step response, and you'll see that it will oscillate for a very long time. Okay, so what do you do if you're designing the suspension? You want to make sure that it's going to settle back very smoothly. Okay, so all these things are used in different systems, just to give you some perspective. All right. Okay, so now if we were to plot for another value of alpha, which is lower, let's say we plot the same thing for, let's say, alpha 2 lesser than alpha 1. So then what happens is, basically you will have probably something like this. Okay, so it will take a much longer time to settle. Okay. So now you can notice that this particular signal, okay, let me just clear it up and redraw it here, right? So we have a response where, it's like a diminishing sinusoidal wave, okay? So V of t is basically given as some constant, which was, what was the constant here? Yeah, 210 root 2 e to the power of minus 2t sine root 2 t. Okay. Now, where and what is the value of this maximum? Okay. So this maximum point is also called as the peak overshoot. All right. So in fact, when we do the step response, that is the terminology that is used. Okay. Now, what is this value? What is the maximum value? How do you find it?
e raised to minus 2t sine root 2t differential will be equal to 0.
Correct. So what you do is set dv by dt, you set it to 0. Okay. So if you set it to 0, what do we get? Shall we calculate? Can you differentiate this and set it to the 0? What is the differential of this? 210 root 2. So it is a UV form. So let's retain e to the power of minus 2t into root 2 into cos root 2t plus it is minus 2 into e to the power of minus 2t sine root 2t. Correct. So this is set to 0. So then what is the, okay, this is minus. So what is the value that you get here? So you basically have root 2 cos root 2t is equal to 2 sine root 2t. Okay. So basically you can write this as tan root 2t is equal to what? Root 2 by 2, it becomes 1 by root 2. Okay. So what is the value of t which corresponds to this? So basically root 2t is tan inverse of 1 by root 2. So make sure that you are doing it in radians. So set your calculator mode to radians. Okay. Otherwise you will be getting an answer. Alright. So it is important to know. So tan inverse of 1 by root 2. 0.615. So t is given by 0.615 divided by root 2.
0.435.
Correct. So t is 0.435 seconds. Okay. Now what is v of t for 0.435 seconds? So this we have found out. This is 0.435 seconds. Now what is the value of this thing? That is nothing but 202 root 2 into e raised to minus 2 into 0.435 into sine of, again make sure that you are having it in radians, okay, otherwise you will be looking at very wrong answers.
71.805.
Correct. So this value is 71.8 volt. Okay. Right. So this is the way that you can characterize it. So is it clear? So an underdamped system, basically if your system is underdamped, it is just going to ring for a longer time, and if your alpha becomes lower and lower, okay, it just is going to keep ringing for a much longer time. Okay. And so if this is your VM, you can find out what is the settling time. Can we determine the settling time? So V max is 71.8 volt. So settling time for 1%. What is 1% of it? V of t should become 0.7718 is equal to your 210 root 2 e to the power of minus 2t sine root 2 t. Okay. So here again it is like, you know, it is you may find it difficult. It will be a little difficult to solve this. So many times people look at the simulation. Okay. So have you simulated these things in your ECAD lab, RLC circuits?
Yes, sir.
Yes. Yeah. So please try these some of these circuits that we do in class. Please do try to work them out. I mean, try to simulate them in ECAD. So it will. I mean, you'll be able to appreciate it and understand it in a little better way. Okay. So let me give you one problem. So this is something that you can solve it before the next class. Okay. So 3u minus t or 3u of minus t current source. All right, and then we have 1 by 240 farad. Okay, this is VC, and this is IC in this direction. We have 48 ohm. We have a 10 Henry inductor. Okay, and then you have a switch. The switch is going to close at t equal to 0. The switch is closing at t equal to 0, and then you have a 100 ohm resistor here. Okay, and this current is IR. All right, and this current is I here. Okay, so the question is determine IL of t for this circuit and plot the waveform. Okay, so what is important is to basically figure out what is the circuit before t equal to 0 and what is the circuit after t equal to 0. So for t greater than 0, what is the circuit? This current source is not in the picture. You have this capacitor. This resistor is shorted out, so you have only inductor, and then you have the resistors here. So 100 ohm, 10 Henry, and then 1 by 240. Okay. For t less than 0, how does this work? So basically you have this current source, which is 3 amperes, and then you have the capacitor, and you have resistor, you have inductor, then you have this resistor. Okay, so try to solve this problem. Okay, so with this you find out the initial conditions, right? And in this case your B1 will not go to 0. You will have a B1 value and you will also have a B2 value. Okay, and then of course to more accurately plot it, it will be good if you can use LT Spice or one of those circuits. Okay, so please try to solve this. This is one problem. Let me also give you another problem. Okay, so how do you find the thing? So first take use the initial conditions, and you can find out one. You'll get one equation or you'll get one constant, and then use the differential. Okay, take di by dt. Okay, and you can use one of the derivatives to get the answer. Okay, so let's try another problem also. Okay, so this is basically 3 volt. You have 50 kilo ohm, and you have 100 kilo ohm, and you have this capacitor. It is 10 microfarad. This 2 Henry, and you have plus minus. This is 5 u of minus t, and there is a 500 ohm. Okay, so what happens here is basically the switches in the left side. Okay, so it moves to the right side at t equal to 0. Okay, So switch is connected to the left hand side for a long time and moves to the right at t equal to 0. Okay. So one thing is what you need to find out. Okay, here this is the voltage V. Okay, so the question basically find V of t. Okay, and V of t at t equal to 1 millisecond. Okay, and another thing is, this is part A, part B, and also find T naught, which is basically the first value of T greater than 0, for which V equal to 0. That is to say, like if you have an underdamped response, right? So what is going to happen is that V of t is 0 here, right? And the next time it becomes 0 is here. Okay. So what is this value of t naught where it becomes 0? Okay. So that is what you need to find out. So whenever you have this kind of, see here, you can also find out the other maxima. So I'm just jumping here, going back to this old problem. You can also find out the values of time where at this point, and so on, right? At all these points, the derivative is 0. Correct. Not only here, it is going to be 0 at this side, it is going to be 0 here, it's going to be the derivative 0 here, and so on. Now, how do you get these other points, right? So here we took tan inverse of 1 by root 2, okay? So you can, whenever you take tan inverse, see the value repeats with a cycle of 2 pi, okay? So you can just add 2 pi to it and then find the value of t, okay? So in this case, what happens?
Or pi, sir?
Yeah, for tan, what happens? You have it becomes negative, no?
For tan, it is like it repeats after every pi.
Yeah. You're right. Sorry. Yeah, correct. It repeats after every pi. So sorry. Yes, you can basically add pi here. Okay. So it repeats for every pi. I'm sorry. Yeah, you repeat for every pi. So you add pi here, and then you find out the next t. You're right. It repeats for every pi.
So for finding t naught, we can just calculate time period and then we can just solve.
Correct. You in this case it becomes very simple, okay, because there is only one sinusoid. But whereas in the next question that I have given, you will most likely end up with the B1 and B2 value, both of which are not 0. Okay. So it is the sum of the sinusoid and the cosinusoid. Alright.
So then we can also like
you can set the value to 0. Yeah.
Sir, no, sir. We can combine both of them and like it will be like something like beta 1 sin omega t plus beta 2 cos omega t. We can combine them to a single sinusoid with a phase.
Okay. Yes, you can do that.
And then we can use an omega.
Yes, you can.
So because if we have superposition of sine and cos, the frequency will remain the same.
Frequency
right?
will remain the same. Only thing is the resultant will have a different phase.
Yes, sir.
Yeah. So, but here the value of t equal to, where v equals 0 is that point. It depends on the phase. So, that's the thing.
Yes, sir.
So, attempt these two problems and we'll discuss the answer in the next class. So, now what I want to do is I want to move over to the next topic. Basically, till now we have done what is the, we have been looking at the parallel RLC. Okay. So let's also quickly look at the series RLC circuit. Okay. So now what is a series RLC circuit? You have R, L, and a C connected in series. Okay. So many times it happens that you basically have Sometimes you have a parallel RLC network, sometimes you have a series RLC network. Okay, so for a parallel RLC network, the voltage was the same for all the three elements and the currents could be different. Here the current is the same for all the three elements. You basically have VR, you'll have VL, and you'll have VC. Okay, and so this is what we basically have here. All right, so you can write an expression for this. So if there is a certain right now, of course, we are not talking about we are talking about a source free circuit. Okay, so let's say there is some initial condition which is there. All right, so what we can do here is we can just write a KVL equation here and then say that the sum of voltages is equal to 0. So what is this? It is R times I plus L di by dt plus 1 by C integral of I dt equals 0. Okay, so this is very similar to our the equation that we had for our parallel RLC. It was just a little different, right? Because we looked at C dV by dt and 1 over L integral I dt, right? So now let us integral V dt. Okay, so how do we solve this? Basically, you differentiate the whole thing, so it becomes R di by dt plus L d squared I by dt squared plus 1 by C into I equals 0. So now again, what you can basically do is you can it is the same form. So here I of t has the solution, which is a1 e to the power of s1t plus a2 e to the power of s2t. Okay, so you can write the characteristic equation, right? What is the characteristic equation here? So if you reorder the terms, you can write it as L into t squared I by dt squared plus R times di by dt plus 1 by C times I equal to 0. Okay, so in other words, you can say Ls squared plus Rs plus 1 over C, right, equals to 0. So the if you solve this, basically you will be S1 and S2 become something like minus B by 2A plus or minus root of so basically let's write the equation. So minus B plus or minus root of B squared minus 4 times L by C divided by 2 times L. Now this can be kind of brought in and things like that. S1, S2 become what? Minus R by 2L, correct? Plus or minus, you take it under the radical sign. So R by 2L the whole squared minus 1 by LC. Okay. So this is of the form basically S1 and S2 is of the form minus alpha plus or minus root of alpha squared minus omega naught squared, where the alpha is now different. Alpha is defined as R by 2L and omega naught is of course given by 1 by root of LC. Okay, so basically the solution form is the same, right? For overdamped, I mean the alpha and the definition of alpha alone changes. Okay, for a parallel RLC network, it is alpha is 1 by 2 RC. Here it is R by 2L. Otherwise, everything else remains the same. And the solution for overdamped systems, right? Because the whole thing is real. So S1 and I of t. Oops. For an overdamped system, what did we say? The radical remains positive. So alpha is greater than omega naught. So which means I of t is basically given as a1 times s1 e to the power of s1t plus a2 times e to the power of s2t. Similar to our parallel RLC, the only difference is that the alpha value has changed. Okay, and for a critically damped system, the solution is pretty much the same. I of t is e to the power of minus alpha t becomes a1t plus a2. Correct? This is what we saw. Here again it's the same thing. The only difference being that the value of alpha is different. Because it is a second order system, it has a very similar expression. Here we are concerned about the current that is flowing through the loop. And the underdamped system, okay, so the underdamped system can also be written as what? E to the power of minus alpha t. Same thing, b1 cos omega dt plus b2 cos omega, sin omega dt, where, as we very well know, omega dt, omega d is nothing but root of omega naught squared minus alpha squared. Okay, and the only difference is alpha is now r by 2l. Okay, so these are the only differences. So let's quickly, you can try an example. Let's try one problem. Let's say this is a third problem. This is an R, C, and an L. Okay, and the R value is 2 kilo ohm, and this is 1 by 401 microfarad, and this is 1 Henry. Okay, so what is given is I of 0 is 2 milliamp, and Vc of 0 is 2 volt. So what is I of t for t greater than 0? Okay. All right, so let's try to solve this. First of all, let's find out what is the value of alpha. Alpha is given by R by 2L, right? So what is the value of alpha?
Power 3.
1000.
Yeah, it is 1000 second inverse. Okay, very good. What is omega naught? 1 by root LC, which is
20.02 into 10 to the power 3.
20.025, right? Into 10 to the
Yes,
power
sir.
of 3 radian per second. Okay. So now tell me, is this an overdamped or a underdamped or a critically damped system?
Overdamped.
Overdamped?
Underdamped.
Which is greater?
Sorry. Underdamped.
It's an underdamped system. Yeah, omega naught squared is greater than, omega naught is greater than alpha, which basically means that it's an underdamped system. Okay. So now what is the solution? We know that I of t is e to the power of minus 1000 t. And so if this is an underdamped system, what is the value of omega d? Omega d is given by omega naught squared minus alpha squared. So what is the value of that?
$20,000.
It is basically 20,000, right? So the solution becomes B1 cos 20,000 t plus B2 sin 20,000 t. Okay. Now we need to find out the value of B1 and B2, right? So so first of all, you can set I of t. I mean, at t equal to I of 0 is 2 milliamp, right? So for t equal to 0, what happens? Sin 0 becomes 0. You just need to, so e to the power of 0 is also 1. So you have B1 and cos 0 is 1. So B1 becomes 2 milliamp, correct? Or 2 into e minus 3, right? So obviously B1 becomes 2 into 10 power minus 3. Now we need to find out only B2. Now how do we find out? So we have to differentiate. So what is given is Vc of 0. Correct. So I think the direction is like this. Vc is given like this, Vc. Okay. And I is given in this direction. Okay. So you can take the derivative. If I of 0 is 2 milliamp, right? And if you take di by dt, L di by dt is, so I'll just give you the overall view, right? So here this is VL, VC, and let's say if a current is flowing like this is the direction of VR. Okay. So VL can be written as VR plus, and this is in the opposite direction, correct? Minus Vc. Okay. Now Vc of 0 is 2 volt. So Vr is what? 2 milliamp into this resistance value. So 2 milliamp into 2K, right? Minus 2 volt is your VL, which is nothing but L di by dt. So now you can differentiate your I of t and equate it and find the other constant. Okay. So I'll just give you the answer. The answer turns out that B2 is 0, and but please work it out. So final I of t becomes 2 e to the power of minus 1000 t cos 20,000 t milliamps. Okay, but just verify it. I mean, do the entire thing. Let me also give you another question. Okay. So probably this is problem number 4 for today. Let's take this. This is 2 ohm. This is a dependent current source, 3 times Vc. You have another 2 ohm resistor plus minus Vc. This is 5 Henry, and inductor current is in this direction, IL. Okay. The question is, find an expression for this thing for t greater than 0 if Vc of 0 minus is 10 volt. Okay, and IL of 0 minus is 0. IL of 0 minus is 0, and Vc of 0 minus is 10 volt. Okay, so now that you have a dependent current source, you basically need to figure out the equivalent resistance that you see from here. Okay, so that will be the you need to find out the Thevenin equivalent circuit. Okay, or you can also write the expression, because it is 3 times Vc. You can also write an appropriate differential equation. So that is one way to do it. Or you can also write an appropriate differential equation and then find out what is the value of alpha and omega naught. Omega naught will anyway will be set by L and C. So the tip is basically write the differential equation and determine alpha. Okay, so that will be a little easier way to do these things. Okay, or you can also put,
Sir,
this is one way to do it. You can also do a Thevenin equivalent resistance. Yeah, so someone had a question. Oh, the capacitor value, right? I'm sorry, I forgot to write 10 millifarad. Okay, So try to solve these problems and let us see. Okay, and yeah. So the some additional details about the RLC we will kind of see when we get into resonance and so on. Okay, when we look at the parallel LC. Okay. All right. So any doubts? Any questions?
So we have to look at the equivalent resistance across the series LC.
Yes. That's why I gave that arrow mark. You can. So that's one way, or you can just basically write, you know, the differential equations and determine. Both should work out fine. Basically, chop that off, put a test voltage source, okay, and you will see what is the resistance there. All right. Okay. So thanks everyone, and have a nice day.
Thank you, sir.